Ladies and gentlemen, I would like to welcome you to my presentation with the title Influence of Compressed Hydrogen on the Fatigue Behavior of a Ferritic Stainless Steel. My name is Schonborn and I work at the Fraunhofer Institute for Structural Durability and System Reliability, RBF. To achieve the European Union's climate protection goals of climate neutrality by 2050, greenhouse gas emissions must be significantly reduced. This goal can only be achieved if primary energy consumption in the European Union is reduced. As you can see from the graph, in 2016, 27% of energy consumption was in the sector of private households, and a significantly higher share of 73% is accounted by the manufacturing sector. One way to reduce energy consumption and thus decarbonize industry is through the use of renewable energy. At this point, green hydrogen could become very important. In detail, a large amount of energy or hydrogen is needed in the manufacturing sector. For example, in the production of materials, in detail for melting or heat treatment of steel or cast iron. Furthermore, large quantities of hydrogen are currently needed in the chemical industry for the synthesis of basic chemicals such as ammonia, methanol, or plastics. In order to completely convert this branch of industry in Germany to green hydrogen, the capacity of renewable energies in this country would have to be tripled. This can only be achieved by importing hydrogen or derivatives. However, the use of hydrogen requires a specially designed infrastructure using suitable materials for the transport, distribution, or storage of the medium. In combination with metallic materials, hydrogen can reduce the strength, ductility, and the fatigue strength. In detail, the adsorption and absorption of atomic hydrogen in the metal lattice leads to a change in material properties. Cyclic loading of the materials in the medium hydrogen leads to hydrogen-induced material fatigue. Due to the different metal lattice, materials have different hydrogen solubilities and diffusion coefficients, which influence the susceptibility to hydrogen. This brings me to the results of the investigation. Investigations were carried out on a ferritic stainless steel 1.45 to 1, for which I have summarized the chemical composition and material properties on this slide. With a tensile strength of 523 MPa, this material does not belong to the group of high-strength steels. From this point of view, this material not show any particular susceptibility in combination with hydrogen. But more on this on the next slides. First of all, I would like to go into the sample geometries used for the examinations again here. In addition to two unnotched specimen forms, which were used for the strain-controlled and force-controlled tests, two notched variants were also used. The influence of the local stress concentration was investigated on the basis of the mildly and sharply notched specimens. Strain-controlled tests were carried out on these unnotched specimens and the results plotted in the form of the stress-strain curves. Here you can see the results in black for the tests in air and in blue under hydrogen. Compressed hydrogen with a pressure of 50 bar and purity 5.0 was used for the investigations. In addition to the results of the cyclic stress-strain curve in the form of the solid lines, the initial stress curves are also shown as dashed lines. The material is slightly cyclic hardening but does not show any susceptibility to the hydrogen based on these tests. The situation is quite different, however, when the test results are plotted in the form of the epsilon n curve. This plot of the total strain against the number of cycles to crack initiation shows a significant influence of the hydrogen. At the upper load level of 0.8%, a factor of 26 in lifetime reduction under hydrogen compared to air can be observed. This life duration reducing factor decreases with decreasing strain amplitude. At the lowest load horizon of 0.2%, the lifetimes under hydrogen and air hardly differ anymore. This should also be shown in detail on this slide with the application of the stresses depending on the number of cycles. As already mentioned, the life-reducing effect of hydrogen is especially evident at the higher strain horizon of 0.8%. A comparable material behavior can also be observed in the force-controlled tests with the unknown specimens. The experimental results are plotted in form of SN curves, in black for the tests in air and in blue under hydrogen. The lifetime reducing influence of hydrogen can be observed especially at the highest load horizons. This influence depends on the stress concentration and thus on the local stress. With increasing the stress concentration factor, the local stress also increases, which favors hydrogen absorption. The difference in fatigue life between air and hydrogen increases with the load. The greatest difference is observed with the SN curves of the sharply notched specimens shown here. The significant influence depends strongly on the local stress and is hardly visible anymore in the area of the knee point. Elastic plastic finite element simulations were carried out for all tested specimen geometries to evaluate the local influence. The local stresses under hydrogen are constantly plotted in blue, and the fatigue strength results of the differently notched specimen geometries are plotted in the other colors. While in the range of lower stresses, the test results under air and hydrogen are still very mixed, a separation can be made in the upper range. Damage by compressed hydrogen occurs as soon as the stress is high enough and plastic deformation can appear. This finding is independent of the stress concentration factor and thus support effects do not seem to play a role. Conclusion. Green hydrogen has the potential to substitute fossil energy sources. This can make a significant contribution to reducing greenhouse gases. When building up an hydrogen infrastructure, attention should be paid to the material compatibility, especially in the case of high local stresses. Possible susceptibilities to hydrogen should be investigated. Cyclid fatigue strength tests are particularly suitable for this purpose. Analysis of the material behavior under hydrogen are necessary. This is the end of my presentation. Thank you for your attention and thanks to the DFG for founding this project.